Welcome to UVU CS3060 Lecture 9.5, where I discuss paged memory allocation. So what is paging? Well, as discussed in a previous video, in the segmented memory allocation, we divide a process up into partitions. Those segmented partitions are stored in memory in various locations wherever there's free space. The problem we had with segmented memory allocation was that the varying sizes would lead to external fragmentation when we couldn't find a hole big enough to allocate for a particular size. Well, paging eliminates this by creating or dividing physical memory into fixed sized blocks. And these blocks can be anywhere from 512 bytes to 16 megabytes. But whatever the value is, it's going to be uniform for all the frames. And this is usually done in a power of 2. Now, what happens when we have fixed size blocks is we completely eliminate the problem of varying sized memory chunks. Everything is the same, every partition is the same memory size. So this completely eliminates external fragmentation. If we need a block that is 4K in size and our frame size is 4K, and there's a free 4K frame, then the allocation is easy. The whole is perfectly sized for the allocation. This system divides the logical memory also into blocks of the same size. So if our frames are 4K in size, our pages are also 4K in size. There will be a one-to-one relationship between the sizes between pages and frames. Now, of course, this seems rather odd because what if you have a segment that is not strictly 4K? We'll see how that works when we come to what is called a page table. The operating system needs to keep track of all the free frames. Now, also, to run a program, we need to find a certain number of frames. So if the program is size n pages, there needs to be n free frames to load that program in its entirety. When a program is being loaded, a piece of memory is set aside called a page table. And that page table identifies where a particular page is located within a frame of physical memory. So it helps translate logical to physical addresses by translating logical pages into physical frames. We'll also see that the backing store likewise needs to be split into pages to maintain the equivalent nature. But again, when we do split up the backing store into uniform page sizes, we eliminate external fragmentation. We still have a problem. In fact, the problem becomes a little bit more pronounced with internal fragmentation while we're dealing with paging. So the way this works is the address that is generated by the CPU, we call this the logical address, is divided into two pieces. The first piece is the page number, but probably the more critical part here, and the one we measure things by, is the page offset. The page offset is the lower n bits of a particular logical address. Let's talk in concrete numbers. Let's say I choose a page offset of 12 bits in size. A 12-bit page offset allows me to address a 4 kilobyte page, numbering 0 through 4095. So if I have 12 bits that I am allowed to index within my page offset, everything that remains will be part of the page number. Now let's say my logical addresses are 32 bits in length. Well, if I have a 32-bit logical address minus the 12 bits of the page offset, that gives me 20 bits for a page number. In effect, I'm allowed to have 1 million entries in my page table. So I can divide my logical address space into 1 million separate pages with their particular page offset, 4K, and then use a million different frames to keep my data within physical memory. So again, for a given logical space, we have the full logical address, 2 to the power of m, in our case 32 bits, and a page size of 2 to the power of n, or 12 bits, or 4K. Here's a diagram that shows what the memory management unit looks like. So the CPU generates a logical address. That logical address is divided up into the two parts, the page number and the offset. The offset is directly copied from the logical address to the physical address offset. So that's the easy part. We just simply take that offset, move it into the physical address, and we're done there. Now the memory management unit takes the page number and performs a lookup into the page table. This is very equivalent to doing an array lookup in the C language, where you use an index value to look at a number or look at a value within an array. That value inside the page table is the frame number where the page is located. The frame number is copied from the page table into the frame value of the physical address, and then the full physical address is used to access the memory location. Another example here, logical memory is divided up into pages. Note that the page numbers are sequential. At least from the CPU's point of view, everything is a contiguous memory address space. There is no breaks here. Now, a page table is also created and associated with that particular process. If I access a value that is addressed within page 1, the memory management unit looks up under page 1 in the page table the frame number, and that frame number is used to find the page within a physical frame. So here we found page 1 in frame 4. The memory address is found, the offset is used, and the CPU can use the data from that memory address. Here's another diagram where we have logical memory, again divided up into contiguous addresses. Let's say, for example, we are trying to access element 9 here, which is represented by the letter J. Well, element 9 is in page table 0, 1, 2, so page table is page number 2. We look up in the page table 2, find the number 1, which is frame number 1, so there's frame 0 and there's frame 1, and our offset is the second element within that particular frame. So there's our data, the letter J. So we can see that in this paging example, all we need to do is use the page number and the offset to find the frame number and the offset. One of the problems we have is with paging is internal fragmentation. We're very fortunate that we've gotten rid of external fragmentation altogether. We don't have to worry about compaction or any of the other issues. But internal fragmentation, while it doesn't require rearranging memory, manages to cause loss of memory. Let's give an example here. We have a page, let's say our system is running with a page size of 2K. Let's say that we have a process that needs to be loaded that is almost 73 kilobytes in memory. Well, in order to allocate this, we'll need 35 full pages of memory, plus we have an extra little over 1 kilobyte of data that needs to be stored somewhere. Well, because every page is uniform, we go ahead and allocate a full page. So with that extra page, we take 2 kilobytes for the page size, and the amount used we take away from that particular page, so a little over 1K. What's left over, this 962 bytes, is the space within the partition, within our page, that is unused. The process should never touch it because it hasn't allocated it. This can be considered wasted space or wasted memory, and is where the internal fragmentation comes. The worst possible fragmentation we can get is to have a full frame that only uses 1 byte, which means nearly the entire frame goes unused and is considered wasted. But on average, across all processes, we see that usually we lose about half of a frame size. So, if we have particularly large frames, like 2 megabytes or 1 gigabyte in frame size, we could have quite a bit of wasted space due to internal fragmentation. So, do we want small frame sizes? Well, perhaps we don't want particularly large ones if we don't need them, but remember that each page table entry takes memory. So if we have a page table, let's take our example we had before where we had 32 bits for a logical address and 12 were used by an offset. That left 20 bits for page tables, meaning 1,000,000 entries. If we reduce that, let's say we go to a 22-bit, 22 bits, leaving only a 10-bit frame, we'd only need 1 kilobyte of page table entries. But of course, our page sizes would be huge. In fact, they would be 4 megabytes in size. So, we don't necessarily want the smallest frame because we'll have huge page tables. But we don't want really big frames because then we will have wasted internal fragmentation. So there's a balancing act that needs to go on here. Choose a frame size that's appropriate for your system. Solaris supports 2 page sizes, 8 kilobyte pages and 4 megabyte pages. On the Intel system, there are page table sizes of 4 kilobytes, 2 megabytes, and 1 gigabyte. Of course, we don't want our systems to be using 1 gigabyte pages when we're loading programs that are only a few megabytes in size. So, on Intel systems, the most common is going to be the 4 kilobyte page size. So now our process view is very different from our physical memory. We've seen that the pages within a process can be scattered all over physical memory in various frames that are not contiguous and very often not even in the right order. But the nice thing about the paging system is by implementation, just by the fact how it's built, a process can only access its own memory. Contrast this to the base and limit. Base and limit, we had to do comparisons to see if our address was outside of our memory address range. We could try to access another process's memory, but base and limit would prevent that. In a paging system, any address that a process generates will reference a particular page number. And as long as that page number is valid, that memory can be accessed by the process. If the page number isn't valid, there are ways of detecting that and then causing the operating system to trap. So let's talk a little bit about free frames and free frame allocation. An operating system will keep track of a list of the free frames. In our example here, the operating system is keeping track of 5 free frames. These 5 free frames can be allocated, and you'll note that this list is not in numeric order. It is not necessary. This actually speeds up insertion and removal from and to the free frame list. Now we have a new process that needs 4 pages of memory. 4 pages of memory means 4 frames. So our allocator will just simply take the top 4 frames and put them into the page table for this process. Now our free frame list is down to 15, frame 15, and our new process has its 4 pages allocated. Again, you'll notice that they're often not contiguous and they're often not in their proper order, but this doesn't matter as the memory management unit will be able to translate from our logical address space to the physical address space. So how is a page table implemented? Well, of course, as mentioned before, page table is kept in main memory. So we have this block of memory that is used for page table and storing frame numbers. The memory management unit has two registers, a page table base register, which points to the top of the page table, and a page table length register that identifies how big the page table is, how many entries there are. So every data or instruction that is accessed by the CPU will require two memory accesses, one for the page table that is kept in memory, and then one for the data or instruction that is stored in memory. Now remember, we talked about CPUs, when they perform memory accesses, generally have to wait for that memory access to come back. This is called a memory stall. Well, introducing page tables now, we have introduced two memory accesses. We're doubling our stall time. Well, just as we solved the stall problem using CPU caches, where memory is temporarily stored on the CPU for quick access, we're also going to create a page table cache. It is called the translation look-aside buffer. So these TLBs are used as caches for the page table. The TLBs are a little bit different than normal caches as they have what is called associative memory. Associative memory is fast lookup hardware. It is very, very rapid in searching through a list of numbers. Traditionally, if you're familiar with an array and trying to look up a value in an array, that lookup is generally in the order of n operations, n being the length of the list. So if I have an array of 20 elements and I want to find an element in that array, it will take me at most 20 iterations to look for that particular item. Associative memory, on the other hand, performs an array lookup in order 1 or constant time, meaning that it doesn't matter where in that particular TLB a page is found, the lookup is always going to be the same amount of time. Now, we do have a problem with context switching. You understand with context switching that we have process 1 that is being stopped temporarily so that process 2 can be run. This requires the memory for process 1 to be disassociated to the CPU, and then the memory for process 2 to be associated with this. Now, this may be as simple as switching process or page tables, but we have a problem with the TLB. The TLB is not directly addressable. And so if the TLB is populated with process 1's page table entries, and we context switch to process 2, something needs to happen to the TLB so that process 2 isn't accessing process 1's memory or page table entries. Well, in any case where this isn't handled, the context switch would have to include flushing the TLB. We would actually have to empty out the TLB so that process 2 could start repopulating this. This is horribly inefficient. If we have a TLB that has 16 entries and process 1 has 8 entries of that TLB filled, and process 2 gets context switch in, if process 2 only uses 8 of the 16 entries, process 1 can still be swapped back in and still have its TLB entries. So there is also a value in most TLBs called an address space identifier. This address space identifier is unique per process and is part of the associative lookup. Most TLBs are on between 64 items to 1024 items within the TLB. When a TLB lookup is made, there's two conditions. Either the entry is there or it's not. When the entry is not in the TLB, we have a TLB miss. On a TLB miss, the steps taken to access the page table in memory are taken. And so we end up having the two memory accesses, one for the page table and one for the value in memory. But when the memory management unit accesses the page table, It also copies the page table entry into the TLB so that any subsequent accesses to that particular page number will have a TLB hit, meaning that it found the entry in the TLB and it's able to access it very quickly. We need to worry about replacement policies. When the TLB is full and we have a new entry that's being accessed, new page table entry that's accessed, which entry should be replaced within the TLB? And we have several ways of doing that we'll go over. We can also cause some of these TLB entries to be made more or less permanent, especially for priority access or very frequent access. We call this wiring down an entry. So here's an example of associative memory. Let's say we have a logical address of 7436 in hexadecimal. Our offset is 12 bits wide, meaning we have a page size of 4K. Our 4K offset for our logical address will be 436. This is 12 bits. The other 4 bits of our particular address is the page number. And in this case, I've separated it here in as 7. Now, the offset, of course, is just simply copied directly from the logical address to the physical address. So here we see 436. The page number first goes to the TLB. Now, in order 1, so in constant time, that number 7 is looked up within this entry, or within the TLB. The TLB will find the page number associated with its frame number and will copy that frame number into the physical address. Now our physical address is the frame number combined with the offset, giving us a physical address of 3436. Again, this particular search is done in order 1 time. It is constant time, and the memory is able to handle this. This is specialized memory built into the CPU. It is considered very expensive, which is why TLBs are generally pretty small. Also, there are some associative systems. In this example, this is a fully associative TLB. Other TLBs will actually be broken into blocks of associative memory. So perhaps we can have 2 blocks of associative memory, which would be two-way associative, meaning that it would have to search one associative memory and then search a second. We still have iterations here, but they are a smaller number of iterations than having to go through the full 4-element list. And those are done usually to save space as well as complexity within a CPU design. If there was a miss, then the whole process of looking this page number up in the page table would be performed. Here's another diagram showing paging hardware with a TLB. The CPU generates a logical address. The offset is copied directly into the physical address offset. The page number first is looked up in the TLB. If there's a TLB, again, it's associative, so constant time access should bring us a frame number on a TLB hit, which we can use in the physical address. If there's a TLB miss, the page table is accessed, the page number is looked up, and the frame in that page number is added to the physical address. Also, this frame is copied into the TLB, potentially replacing some other entry. Once the physical address is fully formed, memory access may proceed. Now, when it comes to TLB, we usually consider the effective access time of that TLB. There are 2 values we need to worry about. The memory access time, we usually measure this in nanoseconds, and the hit ratio of the TLB, which is the percent of times that the page number is found in the TLB. Now, this usually is very related to the number of entries within the associative register. The more entries that there are, the higher the hit ratio is going to be. So the effective access time is calculated by taking the hit ratio times the memory access. So it will just require one memory access if we have a hit. That's the memory access of loading the data from memory. If the inverse is true, so we have the miss ratio by subtracting our hit ratio from 1, this is our miss ratio. If we have a miss, there are 2 memory accesses. Well, we find, if we do a little bit of algebra, that the calculation for this is going to be 2 times the memory access minus the memory access times the ratio, whatever the ratio is. So clearly, we want this ratio to increase because that will decrease our overall effective access time. Consider an access time of 80% with a memory access, an access hit ratio, I should say, of 80% with an access time of 100 nanoseconds. If we take this first formula, our hit ratio is 0.8 times 1 access versus 0.2, which is our miss ratio, times 2 accesses. We get a total of an effective access time of 120 nanoseconds. We can see this improve if we increase, keep our memory access time the same, but improve our hit ratio, where it's at 99% now. We can see that this calculation brings us down to 101 nanoseconds. So clearly, the key here is to improve our hit ratio so that we can improve our effective access time. This brings us to the end of Lecture 9.5, where we discuss paged memory allocation.